In example 33.1, we're going to examine the reflection and refraction of light as it crosses the interface between two optical materials. In this particular case, we have an incident ray that hits the interface between water and glass at an angle of 60 degrees with respect to the normal. We want to calculate the angle of reflection and the angle of refraction in the problem. So the equation that we'll need in this problem is equation 33.4, shown here, which is Snell's law. N sub A is going to be the index refraction of water, which is 1.33, and N sub B the index refraction of glass. Our target variable, of course, is theta sub B in the second part of the problem. In the first part of the problem, we simply want to get the angle of reflection, but that always equals the incident angle, and so theta sub R is 60 degrees. Solving for sine theta B in Snell's law, we get 0.758, and taking the arc sine of this, we get 49.3 degrees for the angle of refraction. Notice that this angle is in fact smaller than 60 degrees, and this is always true on the side of the interface that has the higher index of refraction. And this ends example 33.1. In example 33.2, we're going to consider the index refraction of the fluid in the eye. We're told that the wavelength of the red light from a helium neon laser is 633 nanometers in air, but only 474 nanometers in the aqueous humor inside your eyeball. The aqueous humor is the actual fluid inside the eye, and we're going to calculate the index refraction of this fluid and the speed and frequency of light in the fluid. So the equations that we'll need for this problem are first the definition of index refraction, which is the speed of light in vacuum, divided by the speed of light in the medium of interest, and N is going to be one of our target variables, as will V. We also need the relationship between the wavelength of the light in a medium and the wavelength in vacuum, as given here. And we're going to use the fact that the speed of a light wave is equal to its wavelength times its frequency. So let's begin with this equation and solve for N. We have lambda naught, which is 633 nanometers, and the wavelength in the eye, which is 474, which means that the index refraction is 1.34. The speed is obtained from this equation, rearranging it and solving for the target variable. We get 2.25 times 10 to the 8 meters per second, where of course I use the index refraction I just calculated. And the frequency is going to be the speed divided by the wavelength, which is 4.74 times 10 to the 14 hertz. Notice that this frequency is actually the same as it is in vacuum. In that case, F naught is going to be C over the wavelength in vacuum, and I get the same number. And this is in fact what the eye is sensitive to, not the wavelength. And so the color doesn't change when the light goes through the fluid in the eye. And this ends example 33.2. In example 33.3, we're going to calculate the trajectory of a ray that reflects off of two mirrors that are at a right angle to each other, as shown in this figure. In particular, we're going to find the final direction of the ray relative to its incident direction. This is a very straightforward problem that mostly involves geometry. The only equation that we'll need for it is the law of reflection that states that the reflected angle is equal to the incident angle, where of course these angles have to be measured relative to the normal to the two mirror surfaces, and these are shown by these dashed lines in the figure. So we're ready to begin. Let's assume that the incident ray comes in and hits mirror 1 at an angle theta 1 in respect to the normal to mirror 1. Then it bounces off with the same angle, except on the right-hand side of the normal, and then it's going to bounce off of mirror 2. Notice that this angle from here to here, to the x-axis, is 90 minus theta 1, since this is a right angle. And if this angle is 90 minus theta 1, then this angle also has to be 90 minus theta 1. And the reason, of course, is that this normal is parallel to the x-axis. Since the angle of reflection is equal to the angle of incidence, then this angle is also 90 minus theta 1, which means that the angle that the final reflected ray makes with respect to the positive y-axis is in fact simply theta 1. So if I step back and look at the problem, I notice that my incident ray comes in at an angle theta 1 with respect to a vertical line, and the final reflected ray bounces off at an angle theta 1 with respect to a vertical line, which is the y-axis. Hence, these two rays have to be parallel to each other, but are in fact moving in opposite directions. Another way to look at this problem is to notice, for instance, on the first reflection, that the x component of this incident ray vector remains unchanged, but the y component switches directions. For mirror 2, the y component remains unchanged, but the x component switches directions. So the perpendicular component of the ray vector is reversed upon each reflection. And I have a reversal for each component since I have two mirrors, hence the reflected ray is moving anti-parallel to the incident ray. And this ends example 33.3. In conceptual example 33.4, we're going to consider total internal reflection in a 45-45 90-degree prism like the one shown in this figure. When a light ray enters this prism at a right angle to this large side surface, it hits the two backside surfaces at an angle of 45 degrees with respect to the normal to these backside interfaces. This angle is 45 degrees, and consequently there's total internal reflection. We want to see what happens to the prism if we immerse it in water. So the equation that we'll need for this is equation 33.6, which gives us the critical angle for total internal reflection in terms of the index of refraction internal to the prism, n sub a, and the index of refraction outside the prism. So n sub a is always the higher index of refraction in the process. For the case of the prism sitting in air, n sub a is equal to 1, and solving this equation for the critical angle, theta critical is equal to 41.1 degrees. And this is smaller than the 45 degrees, hence I get total internal reflection. If I immerse the glass prism in water, then the outside index of refraction goes up to 1.33. I need to recalculate the angle, and it turns out to be 61 degrees. And since 61 degrees is bigger than 45 degrees, some of the light refracts through this backside interface. And since the index of refraction is higher on the inside than on the outside, the refracted ray comes out at an angle that's greater than 45 degrees. Call this theta sub b. And this ends conceptual example 33.4. In example 33.5, we're going to see what happens to the intensity of light as it passes through two polarizers as depicted in this diagram. The incident light is initially unpolarized, then it passes through the first polarizer, whose polarization axis is an angle of phi with respect to the vertical. In this case, phi is 30 degrees. Then the light passes through a second polarizer, sometimes called an analyzer, whose polarization axis is along the vertical. We're going to calculate the intensity of the light in between the polarizers and the intensity on the backside of the polarizers. So the equation that we'll need for this is equation 33.7, sometimes called Molasses law, which states that the intensity on the backside of a polarizer is equal to the intensity on the front side times the cosine squared of phi, where phi is the angle between the electric field vector of the polarized light and the polarization axis of the polarizer. Now in this particular case, again the incident light is initially unpolarized, hence there's no preferred polarization direction, and on average only half the intensity makes it through the polarizer, and so the intensity in between the two is simply going to be I naught over 2. But now of course we have a definite polarization direction, which is of course parallel to the polarization axis. As I pass through the second polarizer, the angle between the electric field vector and the polarization axis is again 30 degrees. I need to evaluate cosine squared 30 degrees as per this equation, and I get 3/4. So the total intensity back here is the intensity on the front side, I naught over 2, times this cosine squared of 30 degrees, which is 3/4, so I get 3/8 I naught. Notice that once the light passes through the first polarizer, we have a polarization direction that's parallel to this polarization axis, and then when it passes through the second polarizer, this polarization direction is rotated to be vertical. However, it's rotated at a cost, because every time I pass through one of these polarizers and I'm not lined up with the polarization axis, the intensity of the light falls. And this ends example 33.5.